Okay, so we are talking about vector spaces. So, we have seen the linear combination, linear span of a set. Then we talked about, in the last class we talked about the linearly dependent set of vector, linearly independent set of vector. So, now we will define the basis of a finite dimensional vector space. So, what do you mean by finite dimensional vector space? Let V be a vector space over a field F, then V is said to be finitely generated. We should not use dimension, because dimension we have not defined yet. So, finitely generated V is said to be finitely generated, or it is also called finite dimensional, but dimension we have not defined yet. But anyway, finite dimensional if there exists is the symbol, if there exists a set finite set of vector, if there exists a finite set of vectors, say alpha 1, alpha 2, alpha n, this set which is a vector, such that linear span of this is basically V. So, that means it is generating the set, it is generating the V. So, if such as exist, finite number of vector exist which generating V, then we called V is finite dimensional. Otherwise, if no such as exist, otherwise then V is called. So, V is said to be finitely generated or finite dimensional vector space if there exists a finite set of vector, say n vectors are there, say such that it is generating the V. Otherwise, if no such S exists, it is called, otherwise V is infinite dimensional. If no such S exists, otherwise V is infinite dimensional. Vector space. Okay. So, if no such S exists, then it is called infinite, it is referred to be infinite, but we are concentrating on the finite dimensional vector space. So, we are assuming our there is a set of vectors which generating the this V. Okay. On the basis of that, we define what do we mean by a basis of a vector space. So, basis of a vector space. So, suppose let V a finite dimensional vector space, V be a finite dimensional vector space over field blah blah blah, V be a finite dimensional vector space, then S a set of vectors which is a set of vectors is called a basis, of V if these two conditions satisfy. First of all, it must be independent set of vector. S is linearly independent set of vector, and secondly S must generate V. So, that means linear span of S is basically V. If these two conditions satisfy, then S is called a basis of the vector space V. Okay. So, S has to be linearly independent set of vectors and S must generate V. S must generate V means if you take any beta from V. So, beta should be written as some linear combination of this, and this is true for all beta. This is the meaning of spanning. So, it is basically this set basically generating the whole set, I mean vectors. So, this is called linear, we know this is called linear span. So, if these two conditions satisfy, this S has to be linearly independent and also S must generate S must span the vector, span the space, then it is called a basis of the vector space. We will take some example of basis of some vector space. So, very trivial example is okay, if you take the vector space R3, okay, then if you take this set S to be say 1 0 0 0 1 0 0 0 1. These are all coming, this is a subset of V, if these all are coming from V R3, this is subset of R3, all are, this is alpha 1, alpha 2, alpha 3. Now, we can easily check this is linearly independent, because if we take C1, if we take C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 is equal to 0 vector, then this must imply C1, C2, C3 must be 0. There is only one solution. So, this is linearly independent. And secondly, we have to see whether this can span, this can generate the vectors, all the vectors. So, if you take any other vector, say beta, okay, beta is say ABC, any arbitrary vector, then we can write beta as A alpha 1, A 1 0 0 plus B 0 1 0 plus C 0 0 1. So, this is basically linear combination of alpha 1, alpha 2, alpha 3, and this is true for all beta. Any beta if you take from this vector space, we can show this can be written as the linear combination of these three vectors. So, this is a basis of R3. Okay. So, this is one example. This is very trivial basis. This is called standard basis basically. Now, there we can take another example which is not standard basis. I mean not like 1 0 0 0 1 0. We can see whether this set can form a basis or not. This is not standard because it has two fields. We can take 1 1, we can try that also, but anyway let us try with this. So, this is alpha 1, alpha 2, alpha 3. Okay. So, now we have to check, to be a basis we need to check two conditions. One is this set to be, this has to be linearly independent. So, to check that we can see we have to take this alpha A1 alpha 1 plus C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 to be 0 vector, and we can easily check we get some equation and then we can easily check like C1 plus C2 is equal to 0, C2 plus C3 like this it will get. So, from here we can easily say C2 C1 plus C3 is equal something like that. So, C1, this has only one solution which are 0. So, this is linearly independent set of vectors. And also we can say, see whether this can span the V. So, whether L of S is R 3 or not. So, we take a arbitrary vector A B C from R 3, or these are A B C are real number. Then we can, this also we can verify. We can write this as some beta can be written as some C1 we have used. So, D1 alpha 1 plus D2 alpha 2 plus D3 alpha 3. So, this we can solve the equation, we can get the D1, D2, D3 in terms of ABC. This I am leaving as exercise to you. Okay. So, this is a, so this is also a basis. This is not a standard basis, this is also a basis of R3. Okay, so now we will talk about how we get the basis. I mean, the question is here we have only 3 elements in the basis. Okay. Now, if you take 2 element, can it be form a basis for R 3? Now, can we have a basis of another element? So, if we take 1 1 1, can it be a basis? Can R 3 have a basis which where number is more than 3? So, all these questions we will answer now. So, that means, if what is the meaning of this R 3? So, what is the meaning of R 3 with the number of element in the basis? Question is the number of element if you take 2 different bases. Earlier we have taken the standard basis which is having 3 element, here we have another basis which is having 3 element. Now, is it true in general? That means, the two any basis have same number of vectors or not. So, these are the question we will answer now. So, for that let us first have some theorem. First one is called replacement theorem. So, this is called replacement theorem. Why it is called replacement theorem, we will come to know. We are replacing some of the member from the basis. Okay. Let me just state the theorem, then we will prove the theorem. So, the statement is, let us again the same story, let us take a vector space over a field F, okay, and let this alpha 1, alpha 2, alpha n be a basis of this vector space V over F, and we have a non-empty vector. So, if this is a basis and beta is a suppose beta is a non-zero vector, okay. So, if beta be a non-zero vector, so if this is a basis, then beta can be written as the linear combination of this. So, beta will be written as this, some C 1 alpha 1 plus C 2 alpha 2 plus C j alpha j plus C n alpha n. Okay. And since it is non-zero vector, so not all C i's are 0. If it is all C i's are 0, then this will be 0 vector. So, since it is a non-zero vector, all C I cannot be 0. Now, suppose C j is not equal to 0, C j is not equal to 0. So, that means this contribution is there, C j is not equal to 0. Okay. Then the theorem statement is telling we can replace this C j from here, then this set alpha 1, alpha 2 up to C j minus 1, then instead of C j we take this beta, then alpha 1 alpha C j plus 1, then alpha n. So, these are same number of element, this has n number of element, only thing we have replaced this C j is somewhere here. we have replaced this C j, earlier it was C j, this set is this is our basis, this set, this is our basis. Now, we know this C I is not 0. So, we just want to replace C I by C j by this alpha j by beta, and we want to say whether this will again form a basis or not. The answer is yes, this will also form a basis. The statement is this. So, then this set, this is a this is also a basis of V, that is the statement. Is this clear? So, very easy, we take a basis, now we take a vector. Now, since this is a basis, so any vector can be written as linear combination of this, and this is a non-zero vector. So, since this is a non-zero vector, so in this linear combination at least one of the C I must be non-zero. So, we take this C j is non-zero. Suppose if C j is non-zero, then in this basis we are just replacing that alpha j by this beta, and then we want to see whether this is a basis or not. Yes, this is a basis, we will prove that. So, we have to prove this is again will be a basis. Okay. So, how to prove this? So, let us try to prove this theorem. So, for becoming a basis, we need to show two things. One is this set is linearly independent, first part. So, what is this new set? New set is basically alpha 1, alpha 2, alpha j minus 1, then we have a beta, and then alpha j plus 1, and then we have a alpha n. So, there are n vectors in this set, where beta is nothing but summation of C I alpha I is equal to 1 to n, where C j is not equal to 0, this information we have. Okay. Now, you have to prove this set is a linearly independent set. So, for that what we need to choose? We need to choose a linear combination of this vectors. So, let us take a linear combination in terms of D. So, d 1 alpha 1 plus d 2 alpha 2 d j minus 1 alpha j minus 1 plus d j beta plus d j plus 1 alpha j plus 1 plus dot 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 d n alpha n equal to 0 vector. Okay. So, now we know this beta can be written as this alpha i's. So, if we just replace this beta by alphas, then this will be basically so we have a d 1 form here, and we will get another term from there, which is basically plus d j c 1 alpha 1 plus d 2 we are coming from here, and 1 is coming from there, d j and then c 2 alpha 2, like this. So, the general term is dot 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 plus, if we take the c j, so this will be the c I d I plus, then this is d j c I, then alpha I plus, but for this d j will be, we have only with the alpha I we have only d j c I alpha I plus dot 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 d n plus, so d n is the last term, d n, and we will have another term from here, which is basically this is d j c n alpha n equal to 0 vector. What we need to show? We need to show this is a 0 vector, we need to show all the d i's must be 0. Then this is the linearly independent set of vectors. Now, We know these alpha i's are linearly set of independent set of vector, because this is a basis. So, that means we know this all of these are 0, coefficients are 0. If we know this, so d 1 plus d j c 1 is 0, then d 2 plus d j c 2 is 0, we know this. And then here, from here we know d j c I is 0. Okay. We know d j c I is 0. So, this is basically no, this is not d j, sorry, this is d j, this is c j alpha j is equal to 0. Okay. Now, this way we continue. Now, c j is not 0, because that is the way we choose this, replace this bit. If c j is not 0, then d j has to be 0, because their product is 0. If d j is 0, then all the terms are 0, then we have d 1, d 2, d n all are 0. So, this is the proof. So, this implies d 1, d 2 all are basically 0 scalar. So, if we have a linear combination of these vectors, which will give us a 0 vector, then all the coefficient, scalar coefficient must be 0. So, this is the proof of this set is Li, linearly independent set of vector. Now, we have to show the linear span, whether we can express any vector as a linear combination of these vectors. Okay, this is the second part of this. We want to show this is basically V. Okay. So, for that we have to take a arbitrary vector from here, and then we need to show this is a, this can be written as linear combination of this. So, we can try that. So, we take a arbitrary vector gamma this say x from here, x vector from here, any this is arbitrary vector. Now, we have to write this as a linear combination of this. Now, x is a vector, and we know this was a with the alpha j, this is a basis. So, x can be written as some summation of some a I alpha I is equal to 1 to n. Okay. So, now we can write this as a 1 alpha 1 plus a j minus 1 alpha j minus 1 plus a j alpha j. Now, alpha j we can replace as this. So, how we can write this in terms of beta? So, alpha j can be written as, so this we have to write it as, so we have to just do this. So, we know this C j alpha j is basically beta minus of summation of C I alpha I, where I is from 1 to n, but I is not equal to j, because j we have already taken. Now, we know that C j is not a C j is non-zero scalar. So, C j has a inverse. So, if we multiply this by the C j inverse, then this will give us alpha j is basically C j inverse beta minus summation of C j inverse C I alpha I. So, alpha j can be written as linear combination of beta and other vector. So, here we have, sorry, so this is alpha j. So, a 1 alpha 1 plus a j alpha j plus a j minus a j plus. So, this is j plus 1 alpha j plus 1 like this. Okay. Now, this alpha j can be written as the linear combination of beta and other vector. So, that means, if you replace this this by this expression, then this will be some summation of some say b i's alpha i's I is equal to 1 to j minus 1 plus b j beta plus again b I alpha I is equal to j plus 1 to n. So, this is a linear combination of this vector. So, that means LS is equal to phi. So, this is a basis, this is a new basis. So, if you replace that alpha by beta, then this will again form a basis. So, this is called replacement theorem. Okay, so, we will use this theorem to prove that if we have a linearly independent set of vector, so that must have at most n number of elements. So, let us just try to show that if alpha 1, alpha 2, alpha n be a basis of a vector space V over R over F, sorry, then this theorem is telling then any linearly independent set of vector in V content at most n vector. So, that means if you take a so how to prove this? So, that means if you take a linearly set of vectors in betas, beta 1, beta 2, beta r, say suppose this is Li, linearly independent set of vector, then this theorem is telling r must be less than n. So, this theorem is telling r cannot be more than n. So, that is why for R 3 we cannot have a basis with more than 3 elements. So, r must be less than n. So, how to prove that? So, any linearly independent set of vector is at most having this n number of vectors if this is a basis. So, how to prove this? So, to prove this we will use the replacement theorem. Okay. So, how to proceed? So, this is a basis alpha 1. So, this is just guideline of the proof. So, I am just giving you a rough idea of the proof. So, how to prove this? So, alpha 1, alpha 2, alpha n is a basis, okay, and we have the set beta 1, beta 2, beta r. These are linearly independent set of vector, non-zero vector. Now, since this is a basis, so this beta can be written as linear combination of these vectors, where sum of the Ci is 0, non-zero. So, then this implies we can replace this by one of these alpha 1, alpha 2, say alpha j, just the last theorem we have proved. Then this is also a basis. Now, if this is a basis, then this beta 2 can be written as linear combination of this, where not all Ci's are 0. If all Ci's are 0, if we have only beta 1, if we have only beta 1, then beta 2 and beta 1 are linearly dependent. That is not true. So, that means this beta 2 can be written as some linear combination of these alphas, where the alpha coefficients are at least one alpha coefficient is non-zero. Otherwise, if all alpha coefficients are 0, then beta 2 is basically some scalar into beta 1, but that is not true because they are linearly independent. So, that means again we can replace this by sum of the alphas. So, alpha 1, say alpha k minus 1, alpha k we can replace, beta 2, then alpha k plus 1 like this, beta 1 like this. Okay. So, again similarly beta 3 we can replace with sum of the alphas, because there has to be some alpha coefficient which is non-zero, because this is a basis again. If this is a basis, beta 3 can be written as a linear combination of this basis. Now, in that linear combination, sum of the alpha coefficient must be non-zero, because if suppose all alpha coefficient is 0, then beta 3 can be written as beta 2 and beta 1. which is not possible because this is linearly set. So, in this way we can replace all the betas, we can replace all the betas. Then now there are two possibilities. Now, if r is less than n, if r is strictly less than n, then we can replace all betas and there are some alpha 1s, alpha, so alpha I r n minus r. So, we replace all betas. So, this is fine, this has no issue. Even we can have alpha is r is equal to n, then we can replace all the alphas. But the problem is, if we assume that r is greater than n, that means if we assume the number of linearly independent set vector r is greater than n, then what is the problem? Problem is we replace all the betas with the alphas, alpha exhaust because alpha is less than betas, and we have some more betas to add here. Okay, that is the problem. So, we have some more betas. So, all the betas are gone, only some more betas are left, if this is the case. Okay, then what is the problem? Problem is, now this is a basis, by replacement theorem we are doing this. So, this is a basis. Now, if this is a basis, then any vector from here should be written as the linear combination of these vectors. So, that will not possible because then this cannot be linearly independent set of vector, then this will be linearly dependent. Okay. So, that is the argument. So, alpha this is not possible. So, r must be this r must be less than n or at most less than equal to n. So, number of linearly independent vector must be less than equal to the number of element in the basis. So, from this we can have a theorem that any two bases, if we take any two bases, this will have same number of elements. So, this is just a quick theorem. Any two bases of a vector space V over R over F have same number of vector in it, same number of vectors. Okay. So, if you take one basis S and if you take another basis S1, we take S1 and S2, if these are two bases, then the cardinality of S1 is same as cardinality of S2, and this is true for finite dimensional vector space, and that same cardinality is called dimension of the vector space. So, how to prove this? This we can prove by the earlier theorem. Now, if this is a basis, then if the dimension of this is say m and if the dimension of this is n, now this is a basis and this is a linearly independent set of vector. So, this implies earlier theorem tells this m less than n and similarly m less than n. So, these two will give us m equal to n. So, that means any two bases have same number of vector in it, and that same number is called dimension of the vector space. We will talk about this in the more details. Thank you.